and in developing new experimental methods for studying these processes. She has also worked to promote the development of small satellites for space science and served as co-chair of the Decadal Survey for Solar and Space Physics. She has an undergraduate degree in Physics and Astronomy and a PhD in Physics from UC Berkeley. She came to Dartmouth in 2002 as a NASA Spacegrant visiting young scientists and joined the regular faculty in 2005.
All right, thank you very much. Thank you. I've actually got some good colleagues at UC Santa Cruz. So, but thanks very much for the invitation. It's definitely a bigger forum than the last time, but feel free to interrupt me during the talk. There's a lot in here. I don't need to get through all of it, but my goal is just to tell you about a couple of experiments that we've been working on at Dartmouth and with my group, and tell you a little bit about how we can study Earth's magnetosphere. So Earth's magnetosphere is the magnetic bubble, sort of protective bubble surrounding the Earth. And today I want to focus a little bit on how we use, use energetic particles to make measurements from low altitude in order to remotely sense what's happening there out in space. So that's kind of the big takeaway. And there's two experiments that we've been working on that kind of use that same technique. So I'll tell you a little bit about both of them.
Point at the projector. Up there. It's up here front and center, like right above us.
She's in her computer.
Yeah, and the thing is in the
okay.
computer. Maybe I was on Zoom. Okay, so as I said, the magnetosphere is the protective bubble that surrounds our planet. So here's Earth. And when I say protect, I mean protect from the solar wind. That's a stream of energetic or plasma coming from the sun that hits our magnetic field and is deflected around. There are also cosmic rays coming from things like supernova explosions, so cosmic radiation, that our magnetic field deflects those particles for the most part. This is a really nice simulation. This is made by the Center for Geospace Storms, which is a NASA what we call Drive Center, and they're simulating Earth's magnetosphere. So work this time. Okay, yes. Going backwards, sorry. I got it now. Okay, so the solar wind drives, so as you can see, even though the magnetosphere protects us from these cosmic things like the solar wind drives our magnetosphere. So it's actually a very dynamic thing. We have large geomagnetic storms and what we call substorms, and these produce things like the aurora and also Earth's radiation belts. So some of you may have gotten, how many people saw the aurora in the past year? Yeah, a few of you. So unfortunately it's been cloudy here a lot of the times when we've had the chance to see the aurora. We're kind of at the end of solar max right now, or maybe starting into the declining phase of the solar cycle. And we're just a few days past the year anniversary of what we like to call the Gannon storm, which was named after one of my colleagues, but also called the Mother's Day storm. So last year on Mother's Day, there was a huge geomagnetic storm, what's called a G5 storm. And this produced really beautiful northern lights. Actually, we may have been too far north here. They saw the northern lights even down in Florida, for example, so which is pretty rare, right? So this was a large event, and we've had a number of, there was another one in October. I happened to be in Maryland, and I saw the aurora down there. So we're in solar max right now, and all of this, things like the aurora are being produced by things that are happening out in space. So this is what we see. I like to say that the aurora is the most visible consequence of our connection to the space environment. And all of the things that are actually causing the aurora are actually happening out here well out in the magnetosphere in what we call the plasma sheet. So talking about two steps in the circulation. As I mentioned, the magnetotail, so that's where energy gets accumulated and snaps back. And then also the radiation belts is one of the places where we get energy deposited. So we have particles in the radiation belts that are traveling at nearly the speed of light. So they're very high energy particles. Okay, so the title of my talk was Remote Sensing from low altitude. So how do you actually remotely sense? I have a movie of this in a little bit later, but the key point here is that energetic particles like to travel along magnetic field lines. With the aurora, we see that, right? The particles come down the magnetic field and they hit the atmosphere and produce the light that we see with the aurora. And that's because particles feel a force from the magnetic field and they follow the magnetic field lines down. And so we can use that to our advantage because we can sense these particles down here close to the surface, even though they came from way out here in the magnetotail, near the equatorial plane. So we can sense the processes that are happening out here. And some of my earlier talks that I gave to some of you, we were actually launching balloons. So there are a couple different ways that you can study from low altitude what's happening. So we were doing balloon experiments where we're actually looking at particles as they're coming into our atmosphere. And we can also use small low altitude satellites, or what we call LEO satellites down here in low Earth orbit, to intercept the particles as they're coming down the magnetic field line.
So was Dave McGall working with you on those balloon projects?
Yep, he was, and actually still working with me occasionally.
He's one of us, the STMs. I'm
Yeah.
a member of the STMs as well as this club.
Yeah, so in fact, he's in Ohio for the radio with HAMSI, amateur radio conference this week.
Oh yeah.
So yeah, he has been, he worked a lot on our balloon experiments, and all these experiments require engineers, right? Because I'm a physicist, I like engineering, but I'm not a true engineer, so we work closely with engineers and our students to design and build these things. So David's also, one of the things he's involved with is, we actually have a citizen science project associated with this project that I'll tell you about. This is a proposal right now. If it gets funded, we're hoping that we'll have a citizen science project. So if anybody here is interested, we're going to be developing ground-based instrumentation, so auroral imagers, and some of the basically space weather stations to make measurements in conjunction with this mission. So if we get funded, I'll let you know, and we'll be developing kits where people can put out magnetometers and auroral imagers, and then link them into the internet so we can collect data from all around the globe, basically. So I'm going to tell you about two different missions that we've been working on to study these different aspects of our magnetosphere. And they have this thing in common, that they use these energetic particles to remotely sense what's happening out in space. And the first one is a small satellite called REAL, which stands for relativistic atmospheric loss electron atmospheric loss. So we're looking at electrons that come into the atmosphere, and what we're interested in is how they get scattered into our atmosphere, what's happening out there in the equator. And then the other one is called CINEMA, which stands for Cross-Scale Investigation of Earth's Magnetotail and Aurora. And this is right now a proposal that we have into NASA that we're waiting to hear about. And this is studying that explosive energy release process from the magnetotail. So I'm going to start with this one, and I'm just going to give you kind of the highlights of these missions, just to give you kind of a flavor of what we're trying to do with these. So just a quick reminder of the radiation belts. So REAL is studying the radiation belts, and sometimes called the Van Allen belts. And this is just a recent NASA mission, well, it's not recent anymore, 10 years ago now, that studied this region of space. So this is a region of space that's filled with particles that are traveling near the speed of light, so they're very energetic. And it extends to about 6 Earth radii or so away, and it has this donut shape, and that's because of the shape of the magnetic field. So these particles are trapped by Earth's magnetic field most of the time, but something is scattering them into the atmosphere. Of course, the radiation belts were discovered by James Van Allen, so they're sometimes called the Van Allen belts. They were actually measured first by the Russian Sputnik 2 satellite, but Explorer 1, the very first satellite that the U.S. launched, discovered the radiation So the citizen science project, one of the ideas is to build these instrumentation that would be put out by citizen scientists on the ground that would link the data in with our satellite data, and then there will also be the data from the satellites themselves, which I'll tell you about, and all of that will be in the cloud so that some citizen scientists and scientists can analyze the data as well. So we haven't gotten funded yet. So if and when we get funded, we'll be deciding on the actual platforms, but it'll all be publicly available through some platform. All right, so the color here is just the intensity as part of the number of particles, and you can see again it's very dynamic. So when we get these large geomagnetic storms, the radiation belts fill with energetic particles, and that's interesting from a physics standpoint. You know, how does that happen? Where do they come from? But it's also practically important because these particles can damage our satellites that are out there in space. For example, the GPS satellites, because they're traveling at nearly the speed of light, and they can interfere with electronics.
So for that, it was like going in and out. Like, what's the time period for like those?
Yeah, it takes. They build up. They can build up over a period of hours actually, in really large events. Typically, it's maybe more like a day. But all of that was over the course of a couple weeks. I think that whole movie. But some of the strongest events, even in a few hours, we can see the number of particles go up by orders of magnitude. And so as that last slide. Go back. So the punchline there was Earth is a particle accelerator. We don't, we think of other astrophysical objects as being really energetic and accelerating lots of particles, but actually that's happening in our own planet. And again, this is one of the things that we can use our local space environment to study the things that are happening out in the universe. And so particle acceleration is one of those things that I'm interested in. So, and all of the magnetized planets in the solar system have radiation belts, and we think exoplanets have radiation belts. So as we discover more planets outside of our own solar system, there's more and more interest in, is there aurora on exoplanets? What is the role of a magnetic field in allowing life to form on a planet? What about radiation belts? Are the radiation belts? Jupiter has really strong radiation belts with very energetic particles because it has a very strong magnetic field. This is radio emission coming from Jupiter's radiation belts being radiated by the particles because it's so strong. Okay, so let me tell you about, and this is just some of the space weather effects of the radiation belts. As I was mentioning, these high energy electrons, they can cause charge to build up on electronics, which then discharges kind of like a little lightning bolt inside your electronics, which is not good. Anybody who's like zapped electronics with their hand knows that that's not good, right? So it can, especially as we miniaturize electronics, they become really vulnerable to these kinds of effects. All right, so we know that there are waves in space. This is actually from Van Allen probes. So this you're hearing the audio. So what you're hearing there is audio. Basically, if you take this signal, this is frequency versus time. These are plasma waves in space, and if you put them into a speaker, that's what you're hearing there. This one is called plasmaspheric hiss. It sounds very like hiss. There are all kinds of a zoo of different waves. The way I like to describe plasma waves is in this room we've got sound waves, right? I'm speaking to you. Those are disturbances of the air in the room. But in a plasma, the particles are also charged particles, so they feel electric forces and magnetic forces. So there's a whole bunch of other kinds of waves after interacting with a wave, if it gets momentum along the field line transferred to it, it can make it much further down the field line, and then it hits the atmosphere and is lost. And so this is how particles get scattered into the atmosphere from the radiation belts. And you know that is interesting physics, but it also, there are impacts on our atmosphere. These particles, they don't get down to the surface and affect us, but they can destroy ozone. So there's interest in understanding their impact on our atmosphere.
What are these particles?
They're electrons, the ones that we're looking at. There are also protons as well, but the primary ones that we're observing are electrons. Actually, for this first experiment, it's purely electrons. This is a plot of what this kind of looks like, right? So this is actually X-rays produced by the electrons when they come into the atmosphere. So this is something that our previous balloon experiments measured. And this is versus time, X-ray count rates. This is only, you can see this is like 2 seconds of data, or sorry, 2 minutes of data here. And you see these big bursts of these particles that come into our atmosphere. And something is kicking them in this really bursty fashion like this. And so they can be really intense. So this is what those bursts of what we call precipitation. It's kind of like rain, except it's particles, electrons raining down onto our atmosphere. And this is what we're studying with our first satellite. Yeah.
If the particles continue to be very intense in hitting the Earth's atmosphere, would it completely destroy the ozone?
So it can eat away at the ozone, but the fluxes aren't. I mean, I think ozone is constantly also being replenished. So for when you get a very large event, you can see a big depletion in the ozone, but it kind of repairs itself. But it is one of the inputs and one of the impacts on the atmosphere that people are interested in. That atmospheric chemistry is not my specialty. So I just study the particles and try and understand how many of them are coming in and what are their energies. And then there are chemists, atmospheric scientists who study that part. One of the things important about the high energy particles is they can get a lot lower into our atmosphere. It's still not very low. They get down to maybe 50 or 60 kilometers altitude, so it's still well above, Mount Everest. But that's where ozone is, and so it can affect the ozone. All right, so the first experiment that we're doing is a small satellite. It's about this big, and it's called REAL. And it's what's called, if anybody's familiar with CubeSats, a CubeSat is 10 by 10 by 10 centimeter small satellite, and a 3U CubeSat is 30 centimeters, so it's like 3 cubes put together, so about that big, 30 centimeters in this dimension, and then 10 by 10. And this is a particle detector here, and we're measuring electrons, and these units here are what we call electron volts. It's just a unit of energy, but you can see the range here from kilo electron volts all the way up to mega electron volts. So that's a factor of 1,000 in energy. So these are relativistic electrons are kind of in the hundreds of kilo electron volt range, to give you a feel for that. So these are traveling at almost the speed of light. This is a CubeSat that we've been building over the last while, and the really cool thing about this instrument is we're measuring these particles really fast. So most of the earlier small satellites they don't have the kind of time resolution that we're measuring, and measuring these different directions at the same time. So we line up our particle detector along the magnetic field line, and we can measure the angular distribution of particles coming in from different directions, and that will tell us something about how the waves are interacting with particles. So this is just a little bit of close-up of the particle instrument. So each of these was actually 3 different instruments in this one instrument, and this is because we're measuring particles over such a wide energy range that you actually need to kind of adapt your detectors to handle these different energy particles. And so there's actually 3 different sensors. This is this one, the middle one, and then the high energies are over here. Actually, the high energies are in the middle because they have a much bigger aperture because there are fewer higher energy particles. So we line up this along the magnetic field, and then we can measure the different directions the particles are coming from. So this is just a picture of what it looks like. This was built at Johns Hopkins University Applied Physics Lab. At Dartmouth, we built a mass model of this instrument. So just to give you a feel, so the whole CubeSat is about 4 kilograms. The instrument is just over 1 kilogram and uses about 4 watts of power.
it's aligned with B. So those arrows represent B?
Yeah, that's right.
Okay.
Yeah, it's easier to see in the previous.
Dr. Millan, could you repeat the question for the Zoom?
Oh yeah, I'm
They can't
sorry.
hear you.
Yeah, so the question was about aligning the satellite along the magnetic field direction. So you can see it here. Here's the dipole, kind of our magnetic field of Earth, and we align that one aperture. So there's an attitude control system on the satellite that aligns that one aperture with the magnetic field. So we see which particles are coming straight down the magnetic field, and then the particles that are coming in at an angle. And it's that distribution, the angular distribution, that can tell us about what's happening at the equatorial plane. So there's a lot of physics involved in that, but how these waves are interacting with the particles. Remember, when the wave comes and interacts with the particle, how much momentum it transfers to the particle along the field determines whether that particle is coming in straight down the magnetic field or if it's coming in. And we want to know that distribution because some of the theories predict what that distribution should look like, and we're trying to test that.
And the cone angle has been the angle off the magnetic field line.
That's right. Yeah, the cone angle is the angle off the magnetic field line that we're interested in, and the particles that actually are going to be lost to the atmosphere are only the ones that are just really, really aligned with the magnetic field. And I didn't talk too much about it, but most of the particles are kind of bouncing back and forth like this, and only the ones that are strictly along the magnetic field can actually make it down into the atmosphere. So it allows us to also tell which ones are going to actually go into the atmosphere and which ones are going to bounce back and be trapped in space.
So the detectors are able to detect the incoming angle just as part of the data along with the energy level?
That's right. So each detector will measure the energy of the particle, how many particles are coming in. So we basically count how many in a certain energy bin, and then if you look at these different apertures here, that's how we get the angle. So we're collecting the count rates in each of those directions simultaneously. And that's the new thing about this experiment. There have been other experiments that were on a spinning spacecraft, and they would measure the angle, but it would take them like 3 seconds to get back around again and measure the full angular distribution. But because we have these multiple look directions at the same time, we're able to get the angular distribution all at the same time. And in particular, for these really fast bursts that I showed in that plot, those big microbursts there, we want to get the angular distribution for an individual burst. So we have to be able to measure that whole angular distribution over milliseconds, tens of milliseconds. Yeah. Okay. So, question in the back.
Robyn,
Oh,
how's the
hey,
orbital trajectory? How was the orbital trajectory determined, and did you have any leeway in that decision making?
Yeah, so that's a good question. The question is, how is the orbit determined? And so we want to be on basically polar orbits because we want to be accessing these magnetic field lines that come down near the poles. That's why we see the aurora near the poles, right? Because that's where those magnetic field lines are coming down and connecting to Earth, is in that polar region. And so we want to be in, so we had, the way it works is we're going to hitch a ride to somebody else's launch, basically, and you give them a range of requirements on what your orbit is, and then NASA tries to find you a launch that meets those requirements. So we're actually going to be on what's called a sun-synchronous orbit. Some of you might be familiar with that, where it's a polar orbit, and it stays fixed in the local time. So the orbit actually precesses around, so we cross different longitudes every day, but we're staying we cross the equator at the same time of day. So for example, we're going to be crossing the equator at 10:30 a.m. and then on the other side. And so each orbit crosses where it's 10:30 a.m. on the Earth. So it kind of follows the rotation of the Earth. So that allows us to make measurements in a specific range of local times, which are important because the sun's over here and the tail's here. And so things are kind of organized by local time in our magnetosphere because we have one two different frequencies we're transmitting at. So we have ground stations in Montana. David McGaw is actually going to be helping set up a ground station at Dartmouth for us to talk to the spacecraft, and then to get our data through a much bigger antenna that's at Johns Hopkins Applied Physics Lab, so that we can get all of our science data down, which is a much bigger set of data. So this is just a test that we did. So yay! So when you launch these things, they're inside a little dispenser, and they get shot out once you actually get deployed into orbit, and then like 30 minutes later we have a timer. So this is part of the timer test that we were doing. This was actually after our vibration testing. You have to shake a satellite because it's going to shake a lot when it gets launched, and then you want to make sure it's going to still work, right? So that's what this test was. But the solar panels have to deploy sort of autonomously when it's on orbit. So we were testing that. So we're currently scheduled to launch in I think July 23rd is the current launch date. So there's another NASA mission called Tracers that's the primary launch spacecraft that's being launched on that launch, and so we're kind of a hitchhiker on that launch. Yeah.
Is there a reason you make it that big instead of making it bigger?
Is there a reason that we make it that big instead of bigger? Yes. So when we first proposed this, at that time, NASA was making you pay for your launch if you were any bigger than this. And with this size, they would pay for it for you. So that was the main reason. But I mean, as you'll see, the other mission that we're proposing, we're using much bigger. They're actually they're 16U. They're still CubeSats, but they're 16U. And in that one, we're just asking for a lot more money so we can, deal with the launch ourselves. Yeah.
What data are you hoping to gather from this machine?
So they're particle measurements, and we're trying to get that angular distribution at really high time resolution for those bursts of electrons coming. And what we're going to use that for is to test the theories of how these plasma waves are scattering the particles. So basically it's a way of, because if you can go out into space, but it's much, much more expensive to put a big satellite out in space than a little tiny satellite in low Earth orbit. So it's a sort of pretty cost-effective way to do it. And also, it's actually easier to measure this angular distribution from low Earth orbit, it turns out. So we're trying. That's the measurement that's never been done before. Yeah.
Is there a way to turn this into renewable energy source?
Is it a way to turn it into a renewable energy source? No, I mean our solar panels are pretty small. So we're really more interested in learning about our space environments and the environment that, as we start sending astronauts to the moon and maybe beyond, we really want to have a better understanding of what we're dealing with. And right now we have tons of satellites in space, and we need there's interesting physics because we're sort of using this as a laboratory to study plasma waves and how they interact with particles, but also trying to understand that environment where we launch billions of dollars of satellites into all the time. Yeah.
Kind of just off of that, but are you trying to use the plasma waves from the bursting of the tail to turn into energy? Is that something you guys are
No,
looking
we're
at?
just studying the physics of what's going on. I mean, these are all, even though they're really high energy particles, they're going really fast, but they're just electrons. They're very low mass. So the total amount of energy is actually not that significant. But what we're really interested in is actually just understanding the physics of, because these types of processes are happening on the sun, they're happening in Jupiter's magnetic field, and then other places in the universe, and it's very hard to access those locations. And so we're using our local space environment kind of as a way, and it's also, I should have said, it's actually really hard to create these kinds of conditions in a laboratory as well. So we can't really build it in the lab, and so what we do is we use nature as our laboratory, and we make measurements. Yeah.
I was just gonna ask, how in depth has this study gone? Is this just the surface level, or is there way more to basically uncover from this?
Yeah. So the question is how in depth. I didn't spend. So how in depth is this study? Is it just kind of maybe exploratory? I've actually spent most of my career studying these kind of things, like particles getting scattered into our atmosphere from these plasma waves. So we know quite a lot about that at this point because of all those other experiments, not just me, but other groups have done as well. And we're really going after a very specific question for this because it's pretty in-depth. And I want to part of the reason we designed this experiment is because of previous work that's been done, right? So we know the waves are scattering particles. We've already established that with other experiments. Now we're getting at more of the detail, like how is that happening? Okay, so that's real, and that is real. It's built. We're just doing some final testing right now, just sort of simulating what it's going to be like when we're actually flying the thing. And this is our team, and hopefully launch in mid-July from California, from Vandenberg Air Force Base. So we'll keep you posted on that. But since we're getting short on time, I'm going to cut this pretty short, and maybe I'll show you our movie for cinema. Cinema is actually what we call a, so this is the second experiment I've been spending the last few years on. So the basic motivation of this is cinema is studying this explosive release of energy. When we get these big spectacular auroral displays, what's happening out in the magnetotail, how is it stretching and releasing its energy? And that's the kind of goal of cinema. So this is what's called a small explorer. So NASA has different mission lines. It's a small mission, but it's still $150 million. You know, it's like, in NASA, it's a lot cheaper than Mars sample return. So as NASA mission goes, it's a small mission. It's the smallest class. But this is the Explorer program, of course, is Explorer 1 was the first U.S. satellite, and it was called Explorer. And this program was, developed basically in the spirit of Explorer. They're kind of quick development time, roughly speaking, and they're able to rapidly respond to, new questions that are being raised. And there are explorers that are in astrophysics. So some of you may have heard the TESS mission that's studying exoplanets. That was a small explorer. There's another one called STAR that was an X-ray astronomy mission. That's was also another one called RESI, which was studying the sun. So there's been a whole bunch of these explorers, and we're hoping to be the next one. And we were selected. We put in a proposal, and then we were selected to do what's called a concept study. So they give you a little bit of money to actually do some of the engineering work to see if you can actually do this thing. And so that's what I've been working on over the last year with the team, is all of the, putting together what we call a concept study report, which is a much more detailed proposal of this mission. So this is actually 9 satellites, this mission. And they're slightly bigger. They're 16U, so they're about 50, I think they're 30 kilograms, so maybe 50 pounds or so. And this would launch, if we get selected, it would launch probably in 2029, so it'll take us a few years to develop it. But we were just told a couple days ago that they're going to delay the selection until, I was at NASA headquarters 2 weeks ago to do our final presentation to the NASA Associate Administrator to try and give our pitch. So some of the slides you're going to see are from that. And, there's 4 different projects that are competing right now. And we were hoping to find out really soon, but they just told us they're going to delay, probably because they don't know what their budget is right now. So hopefully we'll find out in the next few months whether this is going to happen or not. So if it does, I promise I'll come back and give another talk about it. So this is really, this is another beautiful picture of the magnetosphere. This includes the magnetic field lines of the magnetosphere. And so this would really be the first mission to give us what we call a cross-scale view. So having multiple satellites that are passing through the region, one after the other, allows you to study how the system's changing in time. So that's why we have 9 satellites. So I'm going to, so there's 9 satellites. There's 3 instruments on each satellite. So one of them is the particle instrument, and this instrument is based off of what we're flying on the real satellite. So we're kind of doing a bigger thing now with this same technology that we developed for real. And we also have the auroral imagers and magnetometers on board. So this is a more sophisticated changing in time. And one thing you'll notice here, you see how this black thing is getting bigger and deepening? This is like a big kind of cavity in the magnetic field strength. And what we think is happening to cause some of this, like when the aurora happens, some of the dynamics, is the formation of this big dip in the magnetic field that it's this kind of depletion that becomes unstable, and then the whole thing kind of explodes. And that's what the simulation is showing here. So you see this deepening black thing, and then all this turbulent light stuff happening. And so this is what we want to actually measure, is this large scale structure of the magnetic field. So now instead of studying waves, we're actually studying the structure of the magnetic field itself. And that's what we're actually remote sensing with particles. Because particles pass through the electrons and protons pass through the equatorial plane. They go all the way along the magnetic field of Earth. And they're kind of sensing, they're carrying that information with them about what the structure of the magnetic field was in the equatorial plane. And by measuring that at low altitude, we can actually say something about the structure. I think I'm going to skip ahead because we're getting short on time, but I will show you this. So we call this the magnetic terrain. It's kind of the structure of the magnetic field. And just as an example, you know, here's a dipole, what looks like a bar magnetic field. And here's a magnetic field, what the magnetosphere looks like with this stretched magnetic field, right? So the structure is different, and that's what we're actually going to be using the particles to sense, is that it's really the curvature of the magnetic field that we can measure. And if anyone wants to know how we do that, I can spend more time talking about it. But I want to tell you a little bit about how we, what the mission's doing. So we kind of have three design strategies. One is we use these polar orbiting satellites, so these are also polar orbiting. We have these remote sensing that we're using 3 different types of instruments. And then as you'll see, our constellation of satellites is going to change over the course of the mission. So I have a couple of animations to show, take you through all that. Okay, so this is the animation version of what I showed you before. So when you're on a low altitude satellite, it's in a polar orbit, you're actually crossing these magnetic field lines really quickly. And that means that you're sensing, so these are particles coming from, they move very fast, the particles. So you're actually able to sense this region of space that extends all the way along the magnetotail, this huge region of space. You're actually able to very quickly sample. It takes our satellites about 5 minutes to cross all those magnetic field lines. And that's really fast compared to the time anything happens in the tail. And so we basically get a radial scan of the structure of the magnetic field every time the satellite crosses through those fields. And it happens in both the northern and the southern hemisphere. And so with the particles, we're basically taking radial scans, and one satellite after the other, we can look at how is the Earth's magnetic field evolving over the course of when a storm happens, for example. So this is what we call our string of pearls configuration. And as I said, we're using the particles to sense the structure of the magnetic field, the same instrument that we're flying on real. But we're also using the measuring the aurora. We have an auroral imager on board each satellite, and then also magnetometers can sense an electric current that flows from out in space, out in the equatorial plane, and down into low do a little tiny, well, it's not a tiny, it's actually a pretty decent burn of the engines to change what's called the inclination of the orbit a tiny bit. And what that does is it causes some of those orbits to like drift ahead and some of them to fall behind. So over the 2-year mission, the satellites will go from this string of pearls into what we call our grid formation here, where you have 3 satellites, one after the other, kind of a grid of satellites. And we're doing that, so this is a cross-scale investigation, and we're looking at the time evolution with the string of pearls. So we get 9, actually 18 when you count the southern hemisphere, snapshots of what the structure of the magnetic field is. And then later we can actually see with the grid formation, we're actually getting the spatial scale in the other direction, right? We can look at how big are these, like this big dip in the magnetic field, how wide is that thing? Does it go across the entire magneto tail, or is it really narrow? We don't know anything about these kind of things other than just some magnetic field models that we don't even know if they're correct or not. So so this is kind of an animation of that. So when we're in this grid phase, now we
on the Earth side of things than the sun side of things. But can you briefly describe the difference between a limb, a flare, and a CME?
Yeah, so the question is the difference between a flare, the limb, and a CME. So the limb is just when you're looking at the limb of the sun, the side of the sun. But a flare is the bright flash that we see, and then usually X-rays associated with that as well. We see like a bright physical flash. Sometimes, not always, a CME is coronal mass ejection. Sometimes a big chunk of the sun, I mean it's like thousands of tons, like a really big chunk, gets basically shot off of the sun, and sometimes it can come towards Earth and hit our magnetic field. And that's called a coronal mass ejection because it's ejecting mass. The process that does that is thought to be magnetic reconnection. So that same thing that's happening in our magnetotail, that the tail stretches back and then it snaps. Whatever's happening when it snaps is that same process that we think is happening in flares. In the case of the flare, it's a loop, a magnetic loop on the sun, and it's kind of getting stretched and it pinches off. In that reconnection process, the same thing kind of happens. You get an ejection, and it's the same kind of explosive magnetic energy release. I mean, the conditions are very different on the sun, obviously, but that's actually one of the motivations for studying it in the magnetosphere, is trying to understand that process that then leads to a big mass ejection.
So I think just a quick follow-up is, when's the next Carrington event?
When's the next Carrington event? Nobody knows. Yeah, it could be any time. There was actually maybe 10 years ago or so, there was a near miss. There was a large event that happened that just happened to get sent in a different direction, not towards Earth. The event that happened a year ago was G5 storm. It was actually a pretty big event, but it wasn't quite the Carrington. The Carrington event was an event that I think it melted telegraph wires and
Caused fires.
yeah, and of course, now we're way more dependent on technology than they were back then. And so, but that storm a year ago, one of the things I learned that I didn't even know is that farmers in the Midwest actually depend on GPS to plant their crops. The tractors, they actually do precision down to the centimeter planting, and that storm disrupted their planting season, and it was something like $500 million loss to farmers in the Midwest because GPS was disturbed. And then the reason GPS gets disturbed is actually because our ionosphere, the ionized part of our upper atmosphere, radio signals are affected when they go through the ionosphere, and it causes errors in the GPS signals which are using radio. So those large storms have a lot of sort of practical effects, including wires, but other effects on airline, especially crew. So a lot of airplanes were diverted during that event, and they didn't go over the poles because they're more exposed to cosmic radiation than the poles. So there's a lot of prediction that happens. If anyone's interested in, there's the Space Weather Prediction Center has a nice website on that. See that? Let me go here and then I'll come back here.
Yeah. How far apart do the satellites have to be in order to get a correct reading and be able to give you correct data?
From the
just how far apart do they have to be in general, and how far above
the satellites
are they? Yeah.
So these satellites are, the question is how far apart the satellites need to be. So because we have propulsion on board, we can actually adjust them. And we're going to start them out about 3 minutes apart, meaning it takes 3 minutes for one crosses a region and the next one crosses the region 3 minutes later. And then we're going to separate them to 5 minutes after that. And the reason for 5 minutes is because we have 9 of them with 5-minute separation. Then when the one in the southern hemisphere, the last one's crossing, the first one in the northern hemisphere is crossing. And so we get a continuous view of the tail for like 45 minutes, right, one after the other. Every 5 minutes we get one of these radio snapshots, and we cover it for like the whole 45 minutes when all the satellites are on the main side. The orbits of these low altitude orbits are about 90 minutes. So it takes about an hour and a half to go around once.
So there's a solar explorer mission that's basically scraping into the upper atmosphere of the sun.
Yeah.
Does that carry any equipment to detect these magnetic separations and reconnections?
Yeah, so that mission, the question is about the mission that's scraping the sun, so touching the sun, we sometimes say. So that's actually a much bigger mission. I think that was close to $1 billion mission, but it's called Parker Solar Probe, and it's the fastest human-made object ever. something like 8 or 9 solar radii away from the surface of the sun. It's really close. Incidentally, that Parker Solar Probe, the heat shield of that, if you look at it, it's got this big heat shield, and the surface temperature of the heat shield is like 2,000 degrees. And the instruments right behind it have to be at room temperature. It's like a marvel. They actually won a bunch of engineering awards because it's just crazy. So they're actually studying the solar wind more, but one of the things they have been able to study some of the aspects of how the sun's corona gets accelerated and heated, right? The sun's corona is actually really, really hot, and nobody understands why it's that hot. And so they are actually, with Parker Solar Probe, doing some of the measurements. They don't actually have an imager looking at the sun because it would just be blinded. It's just so close to the sun. But they have a bunch of particle measurements. So they're mostly measuring solar wind and the particle fields, like the magnetic field, but very close to the sun. So they're studying how the solar wind gets accelerated after it gets released from the sun is the main goal of that mission.
Yeah. I was curious if it varies, like when there's a CME or something coming toward us from the sun. I think it can take a few hours, but does that vary in like the kind of disturbance that's happening?
Yeah, so the question is how long does it take for a CME to reach us, basically? So the bulk of the mass actually can take like a couple of days to get to us, but there are really, really energetic particles that are traveling at nearly the speed of light, and you probably know the sun is like 8 minutes away from us, right? So those particles arrive in like 8 minutes, those very high energy particles. So the effects on astronauts, for example, those high energy particles, some of them can get down through the poles coming along the magnetic field, and so astronauts kind of have to take shelter. And it will be particularly important when we send astronauts back to the moon and possibly Mars. You know, the moon is inside the magnetosphere only for about a third of its orbit around the Earth, and so a lot of the time the moon will spend outside of the protective bubble of the magnetic field, and so those astronauts could get exposed to that radiation. It's actually one of the big challenges with putting astronauts out there. The mass itself is usually, I think the fastest ones are like a day and a half. So we see something happen on the sun. What we don't understand is what kind of impact, or which are the ones that are going to cause the big storms. You know, we can say like, oh, there was an X-class flare that just went off, and there's a big CME headed our way. Sometimes the impacts are huge. I mean, I think the Gannon storm from a year ago, they knew it was coming, but nobody predicted it was going to be a G5 storm, right? It's kind of like a tornado. They have the scale, like different classes and hurricanes. So G5, they were predicting something like a G3, and it ended up being a much bigger event than, much bigger disturbance than was expected. And I don't think, we don't really know, we don't really have a very good predictive capability. We can see something's coming, say, you know, maybe something's going to happen, but we're kind of like in the 1950s, like in terms of where weather prediction was in the 50s. That's sort of where we are with space weather right now, and we really need to be able to do better predictions because we have a lot of technology that's impacted by it. Yeah.
I was curious if we knew a lot about like how these, like specifically how these particles affect people when they're in space, and if these missions will like be able to help us understand more about that.
Yeah, no, so the question is how do these particles affect people in space? So the electrons that we're studying are really more important for electronics than for people. The heavier particles, like protons, are heavier than electrons. And those, especially the really high energy protons that are coming from the sun or cosmic rays, those are the ones that cause cancer and the radiation effects. So there are a lot of people astronauts wear radiation badges. Actually, pilots and flight attendants wear radiation badges because they're being exposed to more radiation because they're above. The atmosphere is also providing some protection. And they're also airlines, you know, the International Space Station, there's a reason it's not in a polar orbit. And it's in an inclined orbit partly because of the radiation concerns about being near the poles. And so, so they've studied, you know, some effects on the International Space Station, but I think, I mean, think right now, actually, I was just in a meeting a week ago. It was a National Academy's group that's studying lunar, what kind of science we can do on the lunar surface when we go back to the moon as a part of Artemis or other moon landing stuff. And one of the things that we talked about was actually the need to measure the radiation environment better to understand it. We just have never had people there for long enough, and also plants, right? What is the effect? We want to grow food or whatever on the moon, and do we need to actually use? People are talking about using the lava tubes that are there to actually go inside because it's more protected from the radiation than being out on the surface. So there's a whole astrobiology effort also in NASA that studies the effects on biological systems, but the radiation environment, we're trying to characterize it and understand what kinds of things might lead to a much harsher radiation environment, and the radiation levels get all bumped up. Yeah.
What excites you most about the data that you might get from these missions?
From these missions, yeah. So the question is, what excites me most? So first of all, what excites me most about REAL is launching the thing, because I'm excited about the data. So we started building that just before the pandemic hit, and which never try to build a satellite during a pandemic is the lesson that I learned. I mean, it definitely slowed us down, and we had some people leave, and then we had to. There wasn't room for some original launch for Super Beyond, so then we had to wait for another launch, and so it's been kind of a long road getting to this point. So we're very excited about launching. So I will be happy if we get data and it works. But I am excited about these measurements because we've just never measured anything. And every time you do an experiment, you plan it for some particular reason, and then you see things you weren't expecting. So I think for me the most exciting thing is what are the discoveries we're going to make that we weren't expecting. Hopefully we'll answer the questions we were asking, but I think the most exciting thing is the unknown. And for cinema as well, with this combination of particles, like when we're measuring, I didn't say this, but we're measuring electrons and protons with cinema. The auroral imaging and the magnetometers all on 9 different satellites. Like that's just never been done before. And we have certain science that we want to do with it, but there's just going to be a huge amount of science that can be done with that data set. Some of it for space weather, some of it for auroral physics, all kinds of different science. So I'm kind of excited to see what the community would do with a data set like that. So hopefully we'll get selected. Any
I'll ask another one if you're.
Yeah.
I was just wondering, the energies you're looking at with electrons, half a MeV, you're pretty near the mass of the electron of that. Are there any anti-electrons in the space environment?
Yes,
And
actually.
do you ever get a collision, an annihilation?
Yeah, I mean, in our atmosphere there are. And so actually one of the things, if I had, was giving a talk on Beryl, the balloon data that we saw, one of the things that we always see with Beryl is the 511 kiloelectron volt line that's actually produced by electrons and positrons colliding. So cosmic rays produce whole showers of particles, and some of them are anti-electrons. And we actually see that, and we use it as a calibration line actually, because we know the energy of that line. And so we see that in the atmosphere, but they're being produced mostly because of interactions in the atmosphere. I think in space, that's a really good question. I don't, I mean, we know that mostly it's matter, right, that's out in space.
When you're near enough the atmosphere with these satellites that you're going to get some scatter of positrons out to the satellites too.
Yeah, it's a really good question because the collisions are not very frequent. I mean, even though we're measuring these particles and we say it's like filled with energetic particles, I mean, it's still pretty empty out there. So that there are not really very many collisions between particles. So it's very possible they're out there. I think it's more likely that they would interact with one of our spacecraft and we might see a little flash of gamma rays or something. I think you actually do get interactions in the spacecraft.
They would be going opposite directions through the magnetic field
Yeah.
line. So if there were anti-electrons and electrons, they would be on collision forces, so to speak, to some
Yeah,
extent.
they would. I mean, I think you just need to have a gamma ray detector to see that though, and it's probably not frequent enough to be able to see it unless you have a big massive
and we hope for lots of future collaborations. And maybe one of these evenings, if we have clear skies right after the presentation, we can actually head up to the observatory. So, and thanks again to our wonderful guests. Thanks everyone.